Hello and welcome to Lecture 1 of the unit of Phys 1101 on work. And the idea of work is going to allow us to extend our ideas about conservation of energy that we met in the last unit to be able to deal with many more types of situations. In the last unit on energy, you probably got thoroughly sick of me saying that we would eventually need a better definition of work before we would understand certain things. And so it is now time for us to start developing that better definition of work. However, it's going to take us a few lectures to fully develop it. Just like if you think back, it took us several lectures to come to our full form of Newton's second law. So this is going to be a similar sort of process as we consider different cases. Part of what's up here is that we know how to use energy to think about when there are gravitational forces acting and when there are spring forces acting, because then we can define gravitational potential energy and spring potential energy and use those in conservation of energy equations. But at this point we have no idea how to deal with any other sort of force when we're dealing with energy, except that somehow forces do work, because work happens when a force is exerted on an object in motion. So work certainly requires that a force is exerted, and it requires that some sort of a displacement happened. So clearly it must depend on the force somehow, and it must also depend on the displacement. But that doesn't get us very far, right? It could be something like this. It could be something like this. It could be something like this, or maybe it's something really complicated like this. And we don't know how the work depends on the force and the displacement. Although I'll say, if you understand dimensional analysis well enough, then you can rule the very complicated one there out. But I'll leave that as an exercise to the reader. So to figure out how to calculate work, we're going to look at a pattern that you might have noticed, and that's whenever a force does work, it results in energy being transformed from one form to another. So here are some examples that we've already seen. When a ball is moving up and down, there's only one force acting on it during its flight, and that's the weight. So weight is doing work because it's acting on the ball while the ball is moving, and it's apparently resulting in transformations of energy back and forth between kinetic and gravitational potential energy. And notice that it's both ways. As the ball goes up, the only force doing work is the weight, and it's resulting in kinetic energy being transformed into gravitational potential energy. And as the ball goes back down, again, the only force doing work is the weight, and it's resulting in the energy being transformed from gravitational potential energy back into kinetic energy. Similarly, when a mass is oscillating back and forth on a spring, in this case where there's no friction, the only force doing work is the spring force, and it's resulting in transformations of energy back and forth between spring energy and kinetic energy. So we're going to define the amount of work done by a force as the amount of energy that it transforms as a result of it doing work. So we're going to write it like this. The work done by a force F is equal to, this delta E is going to stand for the amount of energy that gets transformed as a result of F doing work. So let's look at a simple and familiar example then, using this definition to figure out how to calculate a work from a force and the displacement. Here's this very familiar situation. We've got a ball. It's initially moving down at 2 meters per second. It's 5 meters above the ground. Later, it's just about to hit the ground. It's moving down with some speed that we don't know. And we know what the energy bar chart looks like for this. It initially has some gravitational potential energy. It's moving at the start, so it initially also has some kinetic energy. It ends up having more kinetic energy, and because I've defined my axes down at ground level, it has no gravitational potential energy there. And we know from the last unit in the course that we could use this conservation of energy equation that comes out of this picture to solve for VF if we wanted to. But that's not what I'm going to do, because remember, what we want to do here is establish how much work was done, but more importantly, how that relates to the force and the distance traveled, because that's how we think it should be related. It should be related to those two things, right? Work is done whenever a force is applied on an object that's moving. And so the only force acting on this is its weight. And so we think that's the only force that should do work. And so we think somehow the work done should be related to the force and the distance traveled. And we've defined that our work done should be equal to the amount of energy transformed from one form to another. So what we want out of this is how much energy has been transformed. So think about that. That is the amount of gravitational potential energy that got converted into kinetic energy. So if we just solve for the change in gravitational potential energy, that should be the work done. So here we go. Let's solve. UGF minus UGI is, and if you rearrange that, Ki minus Kf. Okay, and we'll come back to this a few times. This is telling us this is delta UG, right? By our definition of what a delta means, it's a final minus an initial. But this is an initial minus a final, right? So that's negative delta K. And now we think that our work done should equal the change, the amount of energy transformed. Now, there's a bit of an issue here about whether we should set it equal to delta UG or delta K. But the only difference is going to be a negative sign. So I'm going to say the work done by the weight is going to equal, and I don't care about the sign, so I'm going to say the size of this is going to equal the size of delta UG. There's actually a sneaky negative sign we have to worry about later on, but I'm doing this so that we don't have to think about that sneaky negative sign. Okay, well, we certainly know how this works out, because that's our UGF minus UGI, or in other words, mg YF minus mg yi. And look at what that is. You can factor out the mg, YF minus YI. I'll note that this is all absolute values, so I don't care whether it went up or down at the moment. We'll worry about signs later. And so this is mg delta y. Well, that is nothing more than the force, right? This is the force being exerted times the distance traveled, the displacement. So that is going to be our starting definition of a work. A work done by some force F is just the magnitude of that force times, at the moment, I'll say the magnitude of the displacement. And I will say that this is not good enough. This is not a full definition of work, but it's going to be good enough for a start. Let's look at an example of a situation where this new way of thinking about work done lets us calculate something using energy that we couldn't have done before. So let's think about a rocket car. And let's say this rocket car starts from rest and it ignites its rocket motor, and then it moves some distance, delta x, and winds up going at some new VF. And let's say that we know how much thrust the rocket motor is providing. Now, we don't know how to do this using energy methods, and here's why. The energy transformation going on here is that you're converting chemical energy in the fuel into kinetic energy. And while we know how to calculate an initial and final kinetic energy in terms of velocities, or speeds more exactly, we don't know how to calculate a chemical energy. But, here's what the energy bar chart looks like. We're starting with some large amount of chemical energy, and we're ending up with less chemical energy and a bunch of kinetic energy. However, what we do know is that the work done by a force that's connected with this change in chemical energy, so this will be the work done by the thrust, because that is the force connected with this chemical energy being transformed into kinetic energy, should equal the change in the chemical energy. Okay, and I'll just say that for now, we're only going to think about the sizes of these, so we don't have to worry about positives and negatives. Well, where does that get us? Well, our conservation of energy is simply that Echem initial is Kf plus Echem final. And so Kf is Echem initial minus Echem final, or in other words, negative delta E chem. Okay, and that means if we can find the work done by the thrust force, that should equal our change in kinetic energy, or our final kinetic energy, since our initial kinetic energy was 0. So we believe that that should be, I'm going to drop the negative because we know this is positive, so this should be positive. And we know that that work should be the force, so the thrust force, times our displacement. Here is our little rocket car on the runway, and you can see 1,000 meters down the runway are a couple of things to mark that point, 1,000 meters down the runway, so we'll be able to tell when we pass it. And we'll light up the rocket, and away we go. And I'll just mention that there would be in this game, simulation, there would be drag, and also the rocket's mass would change as it burns fuel, but I've set it to ignore both those things. Okay, and I'm just going to back it up to the point where we passed the 1,000 meter point. Here we are, the little guy is standing in the background here, so we're at the 1,000 meter point, and we can see that the speed of the rocket car is 184 meters per second. If you look back at the video of the rocket car, on the left side of the screen you'll see a data display that shows that the thrust was 92 kilonewtons, or 9.2 times 10 to the 4 newtons. The mass of the rocket car was 5,414 kilograms, and we had set things up so that our displacement was 1,000 meters. So we now know enough to solve. We can say our Kf is our work done. So our 1/2 m Vf squared is Ft delta x, or in other words, Vf is the square root of 2 Ft delta x over m. And we get an answer of 184.3 meters per second, which is pretty much what the game or simulation showed us.